Hello everybody, welcome to another exciting edition of HL Chemistry Flipped Classroom. We'll be talking about oxidation and reduction today, and yeah, let's do this thing. Now you know how it goes. I know you're bursting with anticipation here. Make sure, get excited, get hyped, go tell your friends. It's time to start talking about redox. And you know, I think it's going to be good. I think you're going to enjoy it. So oxidation and reduction. One thing I'll say about this unit, terminology can be a little bit confusing. It almost seems like it's on purpose, that they make it confusing on purpose. But we'll get to that. We'll do some things hopefully to minimize the confusion if we can. But many chemical reactions, I dare say most, but not all, involve a exchange of electrons. These are typically called redox reactions, reduction and oxidation, or oxidation reduction, whatever. They're called redox reactions. And the way this is defined is gaining electrons. Something that gains electrons has been oxidized. So gaining electrons is known as oxidation. Losing electrons is known as reduction. So I know right away that probably maybe seems strange that when something loses electrons, it's called reduced. But that's how it goes. And there's a little saying to help remember this. We got our little cowardly lion down there to help us remember. Leo the lion goes grr. That stands for losing electrons is oxidation, gaining electrons is reduction. And believe me, we'll see exactly how this all fits in and what's going on with it as we discuss things here. One way to kind of think about it, you know, and I don't know if this is where the word comes from or not, probably not actually, but when something gets reduced, it gets reduced in charge. It becomes more negative because it's gaining electrons. So that's one way to sort of make some sense of it. What we're going to see, IB specifically mentions the syllabus that you should be aware of an alternate definition. And, you know, in science, we can define things in different ways. We can think about things in different ways. The technical definition is the one I already mentioned to you about gaining and losing electrons. The actual original definition, and one that's useful to use in different contexts, like when we talk about organic chemistry, here's a different way to define oxidation, to define oxidation and reduction. It doesn't work in every context, but in certain scenarios, you're going to find this definition to be easier, mainly when we talk about organic chemistry. Oxidation can also be defined as a gain of oxygen or loss of hydrogen, whereas reduction can be defined as a loss of oxygen or gain of hydrogen. So again, these things can be confusing. We'll sort of kind of shelve this one for now until we go back and look at organic chemistry. When we do that, this definition is going to be the one that's going to be good, and it's going to work better for us. For now, let's stick with the electron thing, though. Yeah, as I said, when we study organic chemistry, you may find it easier to think of redox in these terms, and you'll kind of see how that goes when we get there. Okay, so we're going to be doing a lot of assigning of oxidation numbers in this unit. Oxidation numbers can be thought of as the charge of an atom on an atom or an ion. When you look at oxidation numbers as things undergo a chemical reaction, at least some of the elements, at least some of the species involved will have their oxidation number change over the course of an oxidation number. If no oxidation numbers are changing when comparing reactants to products, then you don't have a redox reaction. Basically, what they are is a way to keep track of electron changes. They're kind of a way to account for electrons. And so one of the very first things we're going to learn, the very first thing here is we're going to learn how to assign oxidation numbers to things. It's in your workbook, and it says you should memorize these rules, understand how to find oxidation numbers before proceeding past this slide. All right, good advice, me. Let's take my own advice here and take a look at that workbook page. So, okay. Here is what this page looks like. It's in the very beginning of the redox unit, as I mentioned. In this introduction, I keep going back and forth between the oxidation state or number. You'll kind of see it presented both ways. You can refer to something as oxidation state or oxidation number. That basically means the same thing. Okay, so here are the rules. They're really not. It seems like there's kind of a lot of them. It's probably not as hard as it seems or as terribly complicated as it seems here. But when we see an element, if we're asked to say its oxidation state, it's going to be 0. So O2, Na, Cu, all those have an oxidation state of 0. They are uncharged. Now contrast that with ions. If we have just a monatomic ion, just one atom that's an ion, well, the oxidation state is its charge. So Na plus, that's an oxidation state of +1. S2 minus has an oxidation state of -2. So one thing that's going to be a big topic, you've probably heard me mention it before in class, and I'll mention it again. There's a huge, huge, huge difference between uncharged elements and their ions. Like Na is a perfect example. If you have pure elemental uncharged sodium metal and you throw in some water, it'll explode. You know, take a bite of sodium metal. You're not going to be too happy with yourself in doing that. However, once this thing loses an electron, Na plus, totally harmless. In fact, necessary for bodily function. It's a part of sodium chloride. So please, I would say if you do one thing this unit, pay attention to the difference between something that's uncharged and charged and the gigantic change that happens when that sodium loses that electron. Becomes it's a real jerk when it's uncharged, basically, but when it gets that charge, it's a pretty nice guy. Now, if you're looking at just an ionic substance, without you realizing it, we've already been thinking about oxidation numbers and charges and so forth already. If you're looking at an ionic substance and you're asked to define oxidation states, just figure out what the charge is of the thing, either from where it is in the periodic table or whatever. So in NaCl, the oxidation state of Na here is +1, and Cl it's -1. By the way, this is a mistake, and I'm going to fix it right now. It might be changed on your workbook. IB has this weird picky thing where if they ask you to say the oxidation state, they ask you to write it down, you must put the charge first and then the number, not the other way around like it was there. So in the real edition of the workbook, that'll probably be changed. But all right, Cu2O, if we're asked to say the oxidation state of Cu and O here, oxygen's -2. Now Cu, we can't look that up on the periodic table, but we can deduce, since there's two Cus, the two Cus, each Cu must be +1 apiece. And so the oxidation state of Cu in this compound is +1. In this compound, oxygen's -2. We can tell that by looking at the periodic table. Cu is +2 to balance out the charge. So we've already done stuff like that. We did that last year. We do that all the time. Just a little rule: the sum of the oxidation states in a compound has to be 0. Like that's what I'm doing here. I'm assuming these things have to add up to 0. So that's why Cu has to be +1 here. In a polyatomic ion, though, if we're asked to find those oxidation states, the sum would be the total charge, and we'll look some examples here. So something that's a little different is we haven't talked about charge in terms of covalent substances. So covalent substances really don't form from ions, so we got to do something a little bit different. And this brings up the point: oxidation numbers aren't anything that's necessarily quote-unquote real per se. It's more just a system and a way to keep track of what electrons are doing. So even though covalent substances don't really form from ions like ionic substances do, we can still assign oxidation states in kind of a standardized system, and we can still use it in redox reactions to keep track of electron changes. So it's a model that we can use to help us understand things. So take NO2, for instance. Here's the rules. When you're dealing with a covalently bonded substance, what you should do is you should first, if there's oxygen and or hydrogen present, give oxygen a charge of -2, an oxidation state, I should say, of -2, and give hydrogen an oxidation state of +1, and assign everything else based upon that. So for instance, in NO2, I'm going to give oxygen a charge of -2. Now keep in mind, there's 2 oxygens there, so that's a total of -4. So I'm going to give the N, I'm going to give the nitrogen +4 for its oxidation state. When it comes to CH4, I'm going to give hydrogen a charge, an oxidation state of +1. There's 4 hydrogens though, so that's a total of +4. So to make that sum to 0, the carbon has to be -4. So in this substance, carbon's oxidation state is -4. A weird thing that will pop up just every now and then is sometimes hydrogen will be part of a covalent, or rather an ionic substance, a metal and a nonmetal. In that situation, you have to give hydrogen a -1 charge, just like you would in any sort of ionic substance. So calcium's +2, therefore these hydrogens have to be -1. It's kind of weird, won't see it very often, but just in case it pops up, I'm going to mention it. So sometimes you'll see covalent substances without oxygen or hydrogen in them. In that case, you should give the more electronegative element its typical charge, like the one you'd see on the periodic table, and then base the oxidation state of the other one on that. So, for instance, fluorine is in the -1 column of the periodic table, so we're going to give fluorine -1, that's its oxidation state. That's total -4, so the iodine has to be +4. Another rarity here is the peroxide ion, like in H2O2. There is a polyatomic ion called peroxide, which is O2-2. In that particular instance, oxygen has an oxidation state of -1 instead of its normal -2. Again, a rare thing, but just something we need to be on our toes with when that does pop up. So what we're doing here is we are going to assign oxidation states to these elements. Let me get this guy ready to go here. Okay, let me just do a couple of these with you. Like for A, CDS, cadmium sulfide, I guess. That's an ionic substance, metal, nonmetal. So I see sulfur on the periodic table. It's in the second column, so its oxidation state is going to be -2. So for this one, sulfur's oxidation state is -2. Therefore, I know they have to sum to 0, so the cadmium is +2. So those are my oxidation states there. In B, NH3, okay, remember the rule is we give hydrogen a +1. So that's what I'm going to do there. So if hydrogen is +1, that is a sum total of +3 here. So therefore the nitrogen, to make that equal 0, nitrogen's oxidation state has to be -3 in this case. Let's look at C. So remember the rule is this is a covalent substance. I'm going to give oxygen -2 to start off with. Now that is a total of -6 from these 3 oxygens. So therefore, to make that sum to 0, I'm going to give sulfur an oxidation state of +6. Let's get another one. Let's look at D. All right, now there's a couple tricky things here about D. First of all, it's a polyatomic ion. That's one thing that's tricky about it. But, all right, so oxygen, I'm going to give it a -2. Okay? So therefore, total, from these 3 oxygens, I have -6 from the 3 oxygens. Now this time, since this thing is a polyatomic ion, I need it to sum to -2. So I'm thinking to myself, what number plus -6 equals -2? And of course, that's +4. However, there are 2 sulfurs here. So in fact, each one of these sulfurs, which is what I'm interested in, would have to have an oxidation state of +2. I'm just dividing +4 by 2. So there's 2 sulfurs that are +2 apiece. That's a total of +4. You got -6 from the 3 oxygens. It sums to -2, and everything checks out. So there's my oxidation states there. Another one that I'd like to look at that is a little bit tricky is one like this, KMNO4. All right, let's jot that down here. Okay, so we got three different things here. So what I would do is I would take care of the things that we know. Oxygen basically always has an oxidation state of -2. So we can get that taken care of. And since there's 4 oxygens here, I'm just to keep track, I'm at -8 so far. Now, then we've got these two things. This is just a normal alkali metal with in the +1 column. Manganese is a transition element that can form different charges. What I would do is let's give potassium a charge first because that one's safe. That one's in the +1 column. It can't form more than one charge. So this manganese, which is in the transition elements, and like we've talked many times, they can form lots of different oxidation states. If I look at what's left over, I got a -8, I got a +1. I need another +7 to make this all sum to 0. So the manganese here is going to end up being a +7. So that's my oxidation state on that one. One more example real quick. N. Keep an eye out for elements. Fe, uncharged, there's no ion here, so the oxidation state is 0 for Fe in this case. What I would like for you to do is take a couple minutes and see if you can figure out the rest of these oxidation states, and pause the video for a second and do that, and then start it up again when you've done. Okay, let's run through these real quick and see where we're at on them. This is one of these weird ones where it's ionic, but it's got hydrogen in it. So hydrogen's -1 here, and aluminum's +3. There's a rule about that up above. N2H4, when you have the hydrogen here, we're going to give the hydrogen +1. That's a total +4. So that means I need a total of -4 here from the two hydrogens, but I got to divide that by 2. So nitrogen is -2 here. In this case, elemental diatomic nitrogen, it's 0. In this case, oxygen, we're giving it -2. There's 3 of them. That's -6. The nitrogen has to be +5 so that it sums to -1. We already did that. Normal ionic substance here, aluminum's in the +3 column, chlorine's in the -1 column, so +3, -1. ICl5, this is one of those weird ones where we don't have hydrogen, we don't have oxygen. Chlorine is more electronegative than iodine though, so we're going to give chlorine its normal charge, which is -1. That's normal oxidation state, I should say. But there's 5 of them. That means the iodine has to be +5. Calcium sulfate. There's a few ways you could do this. You could figure out the sulfate ion by itself first, but kind of like the last example I worked through with you, we're going to give oxygen a -2. Let me erase that there. That's a total of -8 from the 4 oxygens. What I would do is I would do calcium next, because that's a safe bet. It's in that +2 column of the periodic table. It's basically always a +2. So I've got +2, I've got minus. Right now my sum is -6. So therefore, to make that all up and make it sum to 0, the calcium has to be +6. H2O2, this is another one of those weird ones. That's the peroxide ion. So in this case, the oxidation state of the oxygens is -1, and the hydrogen is its normal +1. This guy's 0, like we did. Okay, so CR2O7, dichromate ion. Oxygen's going to be -2. That's a total of -14. Therefore, to make it sum to -2, we've got to have +12, but there's 2 chromiums, so the chromiums actually are +6 apiece. Acetate ion. Charge is -1 here. So we're going to give oxygen its normal -2 charge. we're going to give hydrogen its normal +1 charge. So that's a total of -4 from the 2 oxygens. That's a total of +3 from the 3 hydrogens. This all has to sum to -1. And at the moment, actually, it does sum to -1 because +3 plus -4 is -1. So what can we do but give an oxidation state of 0 to the carbon? And that is its oxidation state there. It's 0. So if you have questions about that, ask me next time in class or go back and kind of watch some of the video again, and hopefully it'll make more sense. Okay, so we're going to go back and okay, so some more terminology, oxidizing and reducing agents. If you think about it, redox reactions are all about exchanging electrons, so it's impossible for something to get reduced without another species getting oxidized. So you can't gain electrons unless something else loses it. You got to gain it from somewhere. So they have these things called reducing agents. Reducing agents are things that cause something else to get reduced. So therefore, reducing agents are losing electrons, and they themselves are getting oxidized. So the thing that gets oxidized is the reducing agent. You can have oxidizing agents. Something has got to help something else get oxidized. Something's got to catch those electrons. Oxidizing agents cause something else to get oxidized, and they themselves are reduced. So reducing agents get oxidized, and oxidizing agents get reduced. And I know it's a little confusing, but that's the way it works. And as we go through this and we use it and we talk about it more and more, it will start to get comfortable. It is a little bit odd. So just an example, okay? Take this little reaction here. If we assign oxidation numbers, those are both elements, so there's 0 in the compound NaCl. Na is +1, Cl is -1. So in this reaction, sodium is getting oxidized. Notice it's going from a charge of 0 to a charge of +1. That means it lost an electron. So it's getting oxidized there. Chlorine is getting reduced. Notice what's happening to chlorine's oxidation number. It's going from 0 to -1 on this side of the reaction. So chlorine has gained an electron. Leo the line goes gur. Gaining electrons is oxidation, losing electrons is reduction. So sodium is oxidized, chlorine is reduced. We could also say that sodium is the reducing agent. It's the thing that's giving the electrons to chlorine. Remember, reducing agents get oxidized. Chlorine is the oxidizing agent. It's the thing that's taking those electrons from sodium. It's the thing that's helping that happen. So it's the oxidizing agent. Now, of course, it gets reduced in that process. Clear as mud? Perhaps. Very often it's it's helpful to split redox reactions into what we call half reactions. Half reactions either show the oxidation or reduction portion of the reaction. It's really important to realize half reactions themselves are not complete reactions. You cannot have, it's just like it says, it's a half reaction. It's only half of what's happening. So you don't have a complete reaction unless both half reactions are taking place at the same time. And like all reactions, though, half reactions should be balanced for atoms and charge. That's probably a new thing to you, being balanced for charge. We use little E symbols, E -1, those represent electrons, and those are used to balance charge. So I'll show you a for instance here. Take this reaction here. So you've got chlorine gas plus sodium iodide makes iodine and sodium chloride. So what we're going to do here, if we notice oxidation number of 0, +1, -1, 0, +1, -1. The sodium, +1 oxidation state, +1 oxidation state. The sodium, nothing happened to it, and they're both aqueous here. So sodium is a spectator ion. I'm going to eliminate the sodium. And then we can look at the reactions. iodine went from a charge of -1 to a 0. Oxidation state is 0 here. That means it lost electrons. Chlorine went from an oxidation state of 0 to -1 on this side. That means it gains electrons. So iodide ions, I- are getting oxidized. The element chlorine is getting reduced. So after I strip out the sodiums, I'm left with the iodines. And in my oxidation half reaction, I'm just showing the oxidation take place. I'm starting off with 2 iodide ions. Those are getting turned into elemental iodine, aqueous. And then notice the charge on the left is -2. The charge on the right is 0, but then I add this +2e minus to show those 2 electrons that are being lost. And now the charge is -2 on both sides. And that's what we want. We want the charge to be balanced. Not necessarily 0 on both sides, but balanced. In the reduction half reaction, we've got chlorine going to Cl2, 2 chloride ions. Total charge is -2 over here, so I put the 2 electrons on this side to balance it out. And that's it for this video. Thanks, guys. Again, I know it's confusing, and the half reactions might be more than a little bit mysterious at this point, but we're going to practice a bunch in class, and hopefully we'll all get there. But thanks for watching, and enjoy the rest of your day.